Understanding fluid dynamics is essential to predict how water will behave. One of the most common yet interesting phenomena that occurs is the hydraulic jump. They often occur in rivers, but they can be observed in spaces like a sink. A hydraulic jump is also called a standing wave. Standing waves occur when a supercritical flow meets a subcritical flow. What is the difference between them? Their Froude number. The Froude number was established by William Froude, an English engineer, hydrodynamist and naval architect in the 19th century. The Froude number is a dimensionless number that determines whether a flow is subcritical or supercritical. It represents the ratio between the average flow velocity to the wave velocity in open channel flow, with L being the depth of flow. It's interpreted as the ratio of the inertial forces to the gravity forces in the flow. The Froude number determines whether a flow is subcritical or supercritical. A subcritical flow, seen as tranquil, is dominated by gravitational forces and behaves in a slow and stable way. The Froude number is inferior to 1. A supercritical flow, seen as shooting, is dominated by inertial forces and behaves as rapid and unstable flow. The Froude number is then superior to 1. Hydraulic jumps happen in open channel flows, not confined within a pipe. What is an open channel flow? It's a type of flow with the water surface under atmospheric pressure. The water flows due to the influence of gravity. The most common examples of open channel flows are rivers, streams, but also canals. Specific energy is nothing but the total energy of the flow per unit weight of the liquid. In this case, the liquid is water. When we plot a graph between the depth of the flow and the specific energy, this is what we get. The curve on the right represents the ratio of specific energy in respect to the depth of flow. The dotted line represents the critical depth of flow. The critical depth of flow is where the specific energy is minimal. If the depth of flow is greater than the critical depth of flow, then the flow is subcritical. However, if the depth of flow is less than the critical depth of flow, then the flow is supercritical. For a given value of specific energy, we see that there are two depths, y1 and y2, that are on the supercritical side and the subcritical side respectively. For the same energy, the supercritical velocity is always superior than the subcritical velocity. This is a cross-section to explain. The depth on the left is y1, which is the supercritical depth, and the depth on the right is y2, and that is the subcritical depth. y1 and y2 are also called sequent depths as they represent the same energy. The supercritical velocity is always greater than the subcritical velocity. To compensate for this energy, the depth y1 has to turn into depth y2, meaning the supercritical depth y1 turns into subcritical depth y2. That literally makes the water jump. In this everyday life example, the subcritical flow is the water that has just fallen out from the tap. The area of the hydraulic jump depends on the flow rate, which changes the energy. Hydraulic jumps are designed by engineers to dissipate energy from dam spillways, weirs and outlets. Recreational ones are used by canoers, surfers and rafters. A hydraulic jump is defined as the rise in the level of water. Hydraulic jumps occur when supercritical flow encounters a submerged object such as a dam or weir, throwing the water upward and changing the flow from supercritical to subcritical flow, which causes a jump. An advantage in hydraulic jumps is the ability to dissipate energy in dams, channels and similar structures.